So our last unit, Unit 4, talked about the difference between ionic and covalent bonding. Remember, with ionic, we're looking at a metal and a nonmetal, and they bond through the electrostatic attraction between oppositely charged ions. So your metal gives up an electron, forms a cation. Your nonmetal gains an electron, forms an anion, and this positive and negative attraction, that's what holds these compounds together with that ionic bond. Okay, so ionic bonds are typically solids at room, or ionic compounds are typically solids at room temperature. They have high melting points. They can conduct electricity when dissolved into ions, which we saw in our conductivity tests. Now, covalent is just composed of nonmetals. And nonmetals are held together through the sharing of electrons. So hydrogen has one valence electron. It will bond to another hydrogen, form a diatomic molecule, and both atoms are then stable. So the point of making an ionic bond or a covalent bond is each to try to get to look like a noble gas, to have 8 valence electrons. That's the point of both of these. Now, also with our covalent molecules, we talked about different shapes. This hydrogen would be linear. There's just 2 atoms bonded together. We also talked about trigonal planar, which a trigonal planar would have 1 atom bonded in the center with 3 atoms around, all in the same plane. This boron is actually one of the exceptions. It only makes 3 bonds, so it only has 6 valence electrons. And then we have tetrahedral, which you should know tetra means 4. So that's when you have 1 atom bonded to 3 different atoms, like our methane here. We also had trigonal pyramidal, which is slightly different than our trigonal planar because it makes a pyramid because you have a lone pair on that central atom in addition to 3 bonds to atoms. So this ammonia, NH3 here, this would be trigonal pyramidal. And finally our last shape, bent. Most common example of that is water, because you have 2 lone pairs and then 2 bonded atoms to each of those. Now we also talked about naming ionic and molecular compounds throughout this trimester. Remember, when you name molecular, all you have to do is list how many atoms you have and then use your prefixes. So if we wanted to name this technically, we would say dihydrogen monoxide. Or this we would say nitrogen trihydride. So we use those prefixes. The only time you don't use a prefix with molecular compounds is when you just have one of the first element. Now with ionic compounds, you are trying to balance the charges. So with a sodium, with an NaCl, you name your cation, which is sodium. Chlorine as an anion is chlorine, so chloride. So that one was pretty simple because you had just one cation and one anion. Now, with the naming with ionic, it gets a little more challenging when you have something like this, because you have to determine. So on both of these, you would probably say iron oxide, but you don't know which form of the transition metal iron is used. So what you want to think about is what you do know. You know the charge on oxide. And oxide is 2 negative. So if a 2 negative was up here on both of these, if it crisscrossed down, well, that means this 3 came from here, making this 3 positive. That means this 2, this would have to be a positive 2. So since the charge is canceled, then we don't see any subscript. So iron 2 oxide. So be sure again you use the crisscross method if you have polyatomic ions like a potassium phosphate. Again, you write the symbol of the cation, symbol of the anion. We crisscross, and we cannot change this PO4. That phosphate is made up of a phosphorus and 4 oxygens, so we need that whole thing, so PO4. Now if this charge was 2, we would need to transfer that 2 down, but put in parentheses with the 2 outside. Also what we talked about, or just a little bit kind of with molecular compounds, we talked about intermolecular forces, we talked about dispersion forces, which exist in all molecules. Sometimes these are called LDFs. It's an attractive force between electrons and a positive charge of a nucleus of another atom. We also talked about dipole-dipole. This is if you have 2 polar molecules, you'll have an attractive force between them. And we also talked about hydrogen bonding, which is the strongest of these intermolecular forces. So with hydrogen bonding, if you had water, we know the oxygen end is slightly negative, so we put the Greek letter delta here, and the hydrogen ends are positive. So hydrogen end is the attractiveness between a positive end of one molecule and the negative end of another. So this negative end here is going to be attracted to this positive end here, and this here, that little dashed line is indicating that hydrogen bond. Okay, hydrogen bonds are what account for surface tension and viscosity of different substances. So that would be our hydrogen bond. I think that pretty much wraps up Unit 4. If you have any questions, let me know.